So in this video, we're going to look at a few concept questions around friction. So here's two scenarios. Scenario A, you have a sled that's being pulled horizontally. Scenario B, you have a sled that's being pulled, same mass, still a 40 kilogram sled, but it's being pulled at an angle of 30 degrees here. So our first question is just which one has the larger normal force? Well, if I draw the normal force on scenario A, it would look like this, right? There's Fn. The other forces that I'd feel is, of course, gravity, Fg. There's, of course, this tension force right here. And then there'll be a friction force, and because this sled is sliding, it's going to be kinetic friction force, so it's going to be an FFK. On the other sled here, I've got normal force as well, and I have gravity and a friction force, also a kinetic friction force, FFK, and a tension force, but a difference is that that tension force has two components. So because it's at an angle, I have a tension force that's horizontal, that's Ftx, and a vertical component to that tension force, there's Fty. So if I'm looking for which one has the larger normal force, what I need to do is think about how the forces balance out. So this is really back to Newton's first law, the issue of the net force in the y direction will be zero if the acceleration in the y direction is zero. And that's the case here, right? This sled is actually going at constant speed, so it has zero acceleration in both x and y, but definitely zero acceleration in the y direction. It's not even moving up, right? It's only moving horizontally. So if I look at scenario A, I can compare the y direction forces. So there's the normal forces in y and gravity's in y. And those are the only two y direction forces. So if I have zero acceleration in y, then I have zero net force in y. That means all the forces in the y direction have to equal each other. So Fn will have to equal Fg. They have to balance out. Looking at scenario B, though, I have three forces in the y direction. I have Fn, I have Fg, and I have the vertical component of the tension force. So same situation here, I still have acceleration is zero, and therefore the net force in the y direction is zero, but the forces that I'm balancing are different. So I'm balancing gravity as the downwards force, and it gets balanced out with a normal force, but also a tension force. So it's like tension is kind of helping you out a little bit here. There's these two up forces that are both working together to balance out gravity, which means that the normal force doesn't have to be as large. So which scenario has the larger normal force? Well, that would be scenario A. And that's because in scenario A, the friction force has to do all that work of balancing gravity all by itself. It doesn't get any help from the tension force. All right, so then which one would have the larger friction force? Well, for this, I can use the equation that FFK is equal to, or at least the absolute value of FFK is equal to mu k times the normal force. So the size of the friction force is equal to the coefficient of kinetic friction times the normal force. So both of these will feel the same coefficient of kinetic friction, so same surfaces, but scenario A has the larger normal force. So that means it must also have the larger friction force. So scenario A will have the larger friction force there. All right, here's another situation. Let's say you have a suitcase and you're pushing it along the ground like this. So it's just sort of moving, maybe at constant speed, something like that. But it doesn't matter if it's constant speed. Every surface is made of the same material, but it's rectangular shaped like this. Now, what if you flipped your suitcase on its end? So now you have a much smaller surface area here, and you push it across the ground like that again. How does the friction force change? So I need to take a second and think about this yourself before I tell you. Will the friction force decrease when you flip it on its end? Will it actually increase, or will it stay the same? So this is a tricky thing. If we look at our equation, this would be a kinetic friction force, right? If I drew the free body diagram of the suitcase in either case, it would feel a normal force, would feel an applied force from you pushing on it. It feels a force of gravity. It feels a kinetic friction force because it's sliding, FFK. So that would be the free body diagram in both cases. And a kinetic friction force, FFK, the magnitude of it is always equal to mu k times the normal force. So mu k has not changed when I flip the suitcase on its end, right? This suitcase is made of the same material on all sides. So the coefficient of friction is just about the material, like how rough they are with each other. And the floor is the same roughness and the suitcase is the same roughness on all sides. So we haven't changed mu k. Let's think about how we changed the normal force when we flip it on its end. Well, actually not at all, right? In both of these cases, the normal force just has to balance out gravity. Those are the only two y direction forces here. And the net force in the y direction will equal 0 because the acceleration in y is 0. So the normal force and gravity will just be balancing each other out. When I flip it on its end, I don't increase the mass of the suitcase, so I'm not going to be increasing the force of gravity, so I'm not increasing the normal force or decreasing it. It stays the same. And if the friction force is just mu k times Fn, and neither mu k or Fn have changed, that means the friction force will have to stay the same. Now that feels a little bit weird. A lot of people feel like, wait a second, the surface area got so much smaller here, shouldn't the friction force go down too? So the thing is though, that when you decrease the surface area, you're also increasing the pressure on that surface. So you have less surface area to make a friction force, but because you have all this mass concentrated on a smaller surface, you have more pressure per unit of area. And so those two things actually totally cancel each other out, and you end up with the same friction force as before. So smaller surface area doesn't actually mean a smaller friction force, because when you make something a smaller surface area, you increase the pressure on that area, and it perfectly cancels out. The friction force just depends on the coefficient of friction and the normal force. Right, here's another conceptual example. Let's say you have a girl on a slide, but it's like a tilting slide. So it starts out horizontal, and then you start to tilt it, and you tilt it further, and you tilt it further. And notice in all of these first four cases here, we've got a static friction force. That's the thing that's holding her on the sled. So she's not moving at this moment. So she's still not moving right here. And then eventually you're going to tilt this slide so much that she starts to move. And at that point, it switches to a kinetic friction force. So you can see I've got an FFK here for kinetic friction. She starts to slip. Once she starts to slip, is she going to speed up down this slide? Will she go at constant speed, or will she slow down? Take a second to think about this one for yourself first, too. All right, let's see if we can figure it out together. So if I do a free body diagram of any one of these sort of in-between pictures here, I've got friction force, I've got a normal force, and I've got gravity. It would probably be a good idea to make my coordinate system parallel and perpendicular to the hill. So I'll make y positive this way, and be x positive down the hill. That means that the force I need to split up into components is gravity. So I'd split up the force of gravity here into a component perpendicular to the hill and a component parallel to the hill. So this is FGY, and this here is FGX. Now, if at this moment she's not moving at all, that means her acceleration is 0. So if her acceleration is 0, so AX is 0, so that would mean that the net force in X has to be 0 as well. There's only two X direction forces here, right? There's this friction force, that static friction force, and then there's the component of gravity that's pulling her down the hill. Those are my only two X direction forces. So those two have to balance out if the net force in X is 0. So that means that the magnitude of my friction force would have to be the same size, but the opposite sign, the magnitude of the force of gravity that pulls you down the hill. Now, if I tilt this this is at the moment where she's just about to slip, but not quite, right? If she starts slipping at this moment, then the force of gravity has not actually changed. It will have the exact same components as before. There's going to be the FGY part here, the FGX. Let me just erase a few things so I've got some more room. Move my coordinate system somewhere else. Let's draw it over here. There's Y positive, X positive. Okay, so there's FGY, that hasn't changed. and the x component of the force of gravity hasn't changed, right? Because it's going to be at the same angle here when I'm just at the moment of just before slipping, and then once I slip, I'll be at the same angle. So the components of gravity won't change. But what will change is the force of friction, because once I'm moving, I switch from a static friction force to a kinetic friction force. And the thing here is that, just erase a little bit more, so more room down here. There we go. The thing with kinetic friction is that it's always easier to, the coefficient of kinetic friction is always lower than the coefficient of static friction. Or in other words, once you get to the max static friction force, once you break through that and you break through the max static friction force, your kinetic friction force will always go down. That's you can kind of feel that if you put your hand on the table, you push forwards as hard as you can. Just before you start to slip, you'll feel a big force, and then once your hand starts slipping on the table, you'll feel suddenly it gets easier. You can try that out now if you want to do a little experiment for yourself. But that's generally true of most materials. So the max static friction force, not the static friction force in general, right? Like this static friction force is much smaller than the kinetic friction force, but the maximum static friction force is going to be bigger than the kinetic friction force. And the kinetic friction force is just a constant thing. It doesn't have this weird sort of changing ability. The kinetic friction force, FFK, is easier to solve. It's just going to be mu k Fn, at least the magnitude of it will be. So that's just going to be like a set value, whereas the static friction force can be up to mu s Fn, but it can also be less than that. It's a bit more complicated, right? Kinetic friction is a bit easier. But that kinetic friction force will always be smaller than the maximum static friction force. So what we have here is a situation where you've got this little tiny x direction force slowing her down, and the x component of gravity is exactly the same as it was here when we were not moving a second before. So that means that this x component of gravity must be bigger than the coefficient of kinetic friction. So what that tells us is that the net force in the x direction in this situation, in our sliding situation, must be equal to some positive value. We must have some kind of an AX that way. Some positive number. We know that the net force in the x direction is mass times acceleration in the x direction. That means I must have a positive acceleration. So that's what tells me she must be speeding up as she goes down the slide once she starts to slip. So the answer would be A. She must speed up once she starts to slip. All right, one more question. Let's say you have your erasers on your textbook and you're kind of bored, so you're just like playing around with it, and you slowly tilt your textbook up. You tilt it up to some angle, and you know the coefficient of static friction between your eraser and the textbook is 0.6. Coefficient of kinetic friction is 0.5. You kind of tilt your textbook a little bit, and the eraser does not slide. It just stays on the textbook. Do you have enough information to solve this problem here? Well, the answer here would be no, you don't. And the reason, what you're missing is a key fact. So if I have a tilted textbook here and there's my eraser, it would feel a normal force. It would feel gravity. It would feel a static friction force, right, because it's not sliding. But the thing is, I can't use this equation. I can't say FFS is equal to mu s Fn. I can't say that. I'm just going to put an X through it so you know that's not true there. The reason why this is not true is because I don't know that I'm at the maximum. This equation, static friction force is equal to mu s Fn, is only true when you're at the maximum static friction force, which is basically when the eraser is about to slip, but not quite. So the maximum friction force you can reach. And that's not necessarily the case here. We just tilted the textbook at some angle, right? That's not enough information. Now, what if we add that little piece of information? So we still know the coefficient of static friction, coefficient of kinetic friction. We're going to add the fact that now we are just about to slip, but not quite. So now that tells us that this equation is true. We still don't have like the mass of the eraser or anything like that, But there actually is enough information to solve now because we can use this equation that FFS now is at the maximum, so it will be equal to mu SFN, absolute values, there we go. And in fact, there's actually more information than we need here. We actually don't need to know the coefficient of kinetic friction. That was, this 0.5 is extra. We actually didn't even need that. Only the 0.6 is all we'll need. So let's try solving this one. All right. Let's draw our free body diagram again. Here's our eraser. Feels a normal force. The normal force you need to make sure is perpendicular to your surface. So there's Fn. Go feel gravity. Make sure gravity goes straight down. Gravity is not perpendicular to the surface, but it's just always straight down. Oh, so sorry. There we go. And then you've got the friction force here. It's a static friction force, FFS. There we go. All right, it feels like I need to toss a coordinate system on here. There's y positive, x will be positive going down. You could make that positive going up as well. It doesn't really matter. It feels like I don't have enough information. When I write down my given, really the only useful thing I'm given is mu s is 0.6. I'm also given that mu k is 0.5, but I don't actually need that. It really feels like I need a little bit more information. Like, don't I need the mass of or something like that? I actually don't. Let's try and solve without that. So what you want to do first is, if you do have the mass, you could calculate the force of gravity. But I don't have the mass, so I'll skip that because I can't. I could write down the fact that the force of gravity is just mass times g, but that's really all I know about it. You do have two components here, right? The force of gravity has a component in the y direction and a component in the x direction. So this is FGY and this is FGX. All right, and then I can start writing down, summing up my forces in x and y. So let's start by sum the forces in your y direction. So summing the forces in the y direction, net force in y, there's only two of them. There's the normal force there, and then there's FGY, that component of gravity. Now, I don't know what angle the textbook is tilted at. I know this, I could call it theta, that angle in there. Using a tiny bit of trigonometry, I can see that this is also theta in here. If you kind of want to go through that, imagine that's like 30 degrees here, then this would be 60. That's a right angle in there, so then that would be 30 again. So the angle in here will be the angle in my triangle there. Okay, so it's kind of a nice little triangle. I could kind of do a bit of SOHCAHTOA there. That'll tell me that FGY is going to be mg, that's the size of the force of gravity, times the cos of theta, because it's close to my angle. And for my coordinate system, I can see that y is positive this way, so that must be a negative value there. I can also do FGX while I'm over here. It's going to be mg, that's the hypotenuse here, the force of gravity, and it's far away from the angle, so it'll be sine theta. And FGX is actually pulling me down the hill, which I've set to be positive, so that's a positive value there. All right. The next thing I could do is say, well, I know it's not accelerating in the y direction for sure. It's not like jumping off the textbook or something like that. So that means that the net force in the y direction will be 0. So I can say 0 equals Fn plus FGY, but let's actually fill in what FGY is since we just did that here. FGY is negative mg cos theta. Well, this is kind of nice because it gives me an equation for the normal force. So the normal force must be positive mg cos theta. All right, I don't know m, I don't know theta, but at least it's a nice equation for the normal force, so I'll put a box around it because it looks kind of useful. Let's try summing up our forces in x. I'm going to need to give myself a bit more space here. I'll just erase our components here, but we will remember what they are. Hopefully you have them written down in your notes. All right. Okay, so in the x direction, so if I find the net force in the x direction, so some forces in x. In the x direction, I have two forces as well. I have this x component of gravity, Fgx, and then I have that static friction force, FFS. I can fill in what Fgx is because we had just done that before. Fgx is going to be positive mg sine theta. And we have the static friction force, which we don't know what it is. And I also know that, and so that's my net force in the x direction. But I also know that the acceleration in x is 0. And so therefore, my net force in x will also be 0. So that means I can take this equation here and do something like this. I can say the net force in x is, oh, sorry, actually I can just toss this in as a 0 right away. Net force in x is 0, and that equals the mg sine theta plus my static friction force. That gives me a nice equation for the static friction force. I could kind of rearrange that if I want to here. So I can move static friction to the other side, and I would get FFS is negative mg sine theta. All right, so those two things look kind of useful together. I have the normal force, and I have the static friction force. I have those two little equations there. All right, but we still don't know mass and we still don't know theta. We're trying to actually solve for theta. Well, there's one thing we haven't used yet, and that is the equation for the maximum static friction force. So because I know that this is about to slide, just about to slide, but not quite, that's a really helpful piece of information because it tells me that I can use the maximum static friction force equation. I can say that I'm just about at the point of slipping, but not quite. Just going to make some room for myself here. Gonna have to get rid of my picture. It's a lovely picture. There we go. All right. So because it's just about to slide but not quite, I can say that the absolute value of the static friction force is equal to the absolute value of mu SFN. So that means I can combine these two equations here. I can actually combine my normal force equation and my static friction force equation, and maybe you can see what's going to happen. That mass will cancel out. In fact, G will cancel out too, so I wouldn't even have to know that this is happening on Earth. So it's kind of interesting. Okay, so let's toss this in here. For the static friction force, I get to toss it in over here. I'm taking the absolute value of it, so that is going to kill the negative sign, right? It just makes everything positive. So I get mg sine theta on this side. This side I get mu s, and then times the normal force, which is mg cos theta. And here's where you can notice that a bunch of stuff cancels, right? I can divide both sides by mass, mass cancels. Divide both sides by g, g cancels. And my equation simplifies down to just sine theta equals mu s divided by cos theta. I'm trying to rearrange for theta, so what if I put all the thetas on one side? Maybe I could divide this side by theta, divide this side by theta as well. And that gives me just sine theta over cos theta is mu s. Now sine theta over cos theta is actually a thing. So if you remember from your functions course, you'll remember that tan of an angle is sine of that angle over cos of that angle. If you're taking functions right now and you haven't gotten to this yet, don't worry, you will learn it in functions soon. So tan theta is sine theta divided by cos theta. That means I can replace this sine theta divided by cos theta with a tan theta, just one function for theta, so that's nice. And that'll equal just the mu s is all that's left on this side, right? Because I divided out the cos thetas. To get the theta out of the tan function, I need to use an inverse tan. So I do theta is the inverse tan of the mu s. Mu s is 0.6, so you can plug that number in. So I'm going to inverse tan 0.6, and that gives me 31 degrees. So theta is 31 degrees. Now with significant figures, essentially only one significant figure allowed here, so I have to rewrite that as 3 times 10 to the 1 degrees there. So it's a very rounded number. That's the angle that the textbook must be tilted at.